Hello, everyone. Good evening and welcome to Creative Tech Talks. Our topic today is chaos engineering, and our presenters are Keet and Pubudu. Both Keet and Pubudu are site reliability engineers. They're working for our Norway-based client, who is the industry leader for big data and digital transformation technologies. Keet, is interested in cybersecurity, cloud computing, and distributed computing. And Pubudu's interests are in machine learning and distributed computing. So we will start the talk now. Over to you, Pubudu.
Thank you. Thank you, Kanchana. So today we are going to learn about chaos engineering. So this is our agenda. So this is the things that we're going to talk today. So we'll be introducing you to how this chaos engineering concept started and what is chaos engineering and how this chaos engineering experimenting is different from testing, unit testing and integration testing and QA testing, and what companies are following these practices and why we need to do chaos engineering. And there's a special application called Chaos Monkey. We'll be describing a brief description about that. And also Keith will be describing about principles of chaos engineering. And we have prepared a small demonstration so that you can understand these concepts and the applications better. And finally, we will discuss about challenges faced in chaos engineering. So how this concept started. So in about 2008, the chaos engineering concept started in Netflix. So in 2008, in August, Netflix started to migrate to cloud solutions because previously they had one single data center, and in August it went down, and they had 3 days of 3 days of downtime. Because of that, they had to stop their sales for 3 continuous days. So with this incident, Netflix thought they need to move into cloud solutions because they are now limited by the scalability options because of this vertical scalability is not possible with their current uprising demand. So they thought that they need to move to cloud computing, and since the data center was a single point of failure, they thought moving to cloud solutions would be the savior for them to fix this issue. So, and then they found out that it was not the best solution. It was the best solution, but it didn't work as they intended. As everyone who works on the distributed computing knows that the instances, let's say like a Kubernetes pod, could disappear for various reasons. It could be networking, it could be infrastructure based, or when we use cloud services, these instances could go down because of hardware failures in their data centers. Likewise, so what they have realized that they have moved their problem into single point of failure to multiple points of failures because these random instances disappearing. So they went on a quest to fix this thing for them, and they started hiring senior engineers to tackle down this problem in their production systems. And as a result of this quest, an application was born in Netflix called Chaos Monkey, which is an application to simulate similar instances disappearing, but with more in more expected periods. Like when an instance disappears about in like 3 in the morning, when no on-call engineer is around to look into it, then that's a disaster. So what Chaos Monkey did was choosing up these, recreating this problem of disappearing instances in let's say office hours, where someone can tackle that problem and fix it. So this Chaos Monkey application was on around 2011, and they did quite good for some time. And then in Christmas Eve on 2012, AWS region failure was occurred because Netflix was using AWS services as their infrastructure. They had a very bad time at that time because no one was at office. It was Christmas Eve, and they again went on fixing this kind of failures because this is a bigger problem to tackle than what they have fixed before. So as a result of this, they came up with a new application called Chaos Kong, which is to simulate region failure, artificial region failure, and act upon it to recover their services. So for a region services, the problem is you have to redirect the traffic to a particular failed region to another available region. So at the beginning, this test took like days to complete a single migration. And with the time, with Chaos Kong is like frequently creating this chaos in their system. They learned better ways to fix this thing more faster. So in the beginning, the best case recovery time was about 50 minutes, and they managed to bring it down to 6 minutes with continuous region failure simulations. That's like they were keep practicing and improving their processes to achieve a higher availability. And at this point, there was no discipline called chaos engineering in the world. This was only Netflix who are doing these things in their own house. So in about 2015, they thought that we have learned a lot of good things with our practices, and we need to formulate a discipline. And two engineers in chaos engineering team in Netflix was given this task. Casey Rosenthal and Nora Jones. They went on asking engineers in Netflix, what do you think the chaos engineering principle is? So they gathered information and they formulated a discipline and wrote a book and released it to the world, so that world can know that this is something that they should follow. This is something really important. So after that, they wanted to hire more chaos engineers to run their systems, and they went on finding senior chaos engineers, but they failed to find any senior chaos engineer because the concept of chaos engineering was not established in the world. So what they did was they thought that we need to spread this practice discipline throughout the world. So they start on hosting a community day, Chaos Community Day. First one was on 2015 with about 40 participants, with like important companies like Microsoft, Amazon, Google, Facebook, likewise. And it was a success. And in 2016, they hosted it again. And in that community, Amazon has announced that they have adapted this practice, and it had helped them a great deal to overcome these problems and have higher availability. And in 2017, it became a little bit more popular, and they held a community day with 150 participants. And about 2 months later, Nora Jones gave a keynote on chaos engineering with 40,000 in-person participants and 20,000 streaming attendees. So that made the breaking point of chaos engineering, that the world knew that this new concept is now established in the world. So going forward, so what is chaos engineering? In simple terms, chaos engineering is a discipline of experimenting failures in your production systems and testing your production system's capability of tolerating those failures. Let's say you have a service, microservice deployed in Kubernetes. Let's say Elastic Search cluster. So what will happen? Couple of nodes went down. How Elasticsearch would cater this missing pods, missing instances, how it will handle the load going forward. So this kind of testing is included in chaos engineering. So chaos engineering is controlled and planned experiments. We use the word experiment because the outcome is not known, that you don't know what. So like by killing a pod, you don't know what will happen to the system, how the system will react. And by this, doing this, you will face unpredictable failures. Likewise, if you didn't do any test, the systems will eventually fail at some point for some reason. So you will have these issues by surprise. So you won't be able to act quickly upon this and fixing things. So by doing chaos engineering in your organization, you will be able to see the problems beforehand, they hit production, and resolve them. And also preparing engineers for failures. Because when we are doing chaos engineering like continuously, so this turbulent conditions in production means like this test is not like done once in a year kind of thing. So the chaos should be implemented, inherited in the system, and the chaos should be visible all the time, so that engineers have to work on it before working on anything else, like developing feature or anything. You have to focus first on the reliability of the system, and after that you can focus on feature developing and any improvements beyond that. And by that, it's automatically improves your reliability and makes your system very robust, that the downtime is very less, and it helps to meet SLA by fortifying your systems. So let's say if you have a SLA of 3 nines, like 99.9, then you can only go down for like 43 minutes in a month. So let's say you had a region failure that took 1 hour to resolve, then you are directly out of your SLA and you will owe money to your customers. So bringing that downtime to few minutes would save billions of dollars for your company. And chaos engineering is important to prepare for a game day. Game day is like a hackathon. You decide a scenario to do chaos engineering. You have a target. Let's say like we're going to test our Elasticsearch cluster, and you have some hypothesis on it, and you have all the best persons who knows about Elasticsearch and the code that works with Elasticsearch. Everybody is there, and you inject a planned failure and work together within a fixed time, let's say 1 hour or 2 hour fixed time. You work to resolve that problem. By doing that, a company participants can gain more knowledge about what are the failures can occur with these unpredictable failures occurs within the production system. And what is chaos engineering is not is random chaos engineering experiments. Let's say like experiment running in 3 in the morning when no one is around in the office to to address the failures. And unsupervised chaos engineering experiments, that is like we don't have control over the engineering, let's say, blast radius. So it will affect the customers and create a huge service disruption. That is not what chaos engineering is intended to do. And unexpected chaos engineering experiments, that is like people should be expecting these failures to act upon, because if you are under a very tight SLA, so any failure is gonna cost you money, and it should not break production by accident, and everybody should be alerted before that, and they need to be ready to prevent very large downtimes. And if you have any questions on this, please feel free to raise your hand. I will go forward. So how we will discuss how these chaos engineering concepts are different from testing that the normal testing. Testing is an assertion that is made on a specific condition, that we expect a certain outcome, and it only works to test the code that we have written if it's doing what we intended to do. So it's basically true or false scenario, and since you have already known the outcome, what you expecting, there is no learning in that testing. You already know that it could fail if this happens. And what chaos engineering is characterized as experimentation, because it creates new knowledge and you don't know what outcome, what events that chaos testing would create in your production environment. And it will open up new pathways to look into your system's reliability, maybe some aspects that you have never thought about, to improve the recovery time and get your system very robust. And it's also helping to identify the complexity of your system. Let's say like you have a lot of dependencies in the microservice architecture, and when you code, you might not think about, like as example, you have a program that writes to a Kafka cluster, a particular Kafka topic. So you don't code or you don't write test on what to do when the Kafka topic is deleted by accident. So this kind of scenario will not be covered in a unit testing or integration testing. So this is a pure chaos that chaos engineering will be simulate into your system, and you can only address this by knowing that this disappearance of this particular Kafka topic will create this kind of disruptions in your system, and you need to address these disruptions in a better way. So that's the basic difference between chaos engineering and unit testing. So we'll move forward. So these are the companies that have followed the path of Netflix and adhered to chaos engineering practices. And there are a few links here. You can get these when we share this presentation with you. These links contain good discussions on chaos engineering practices in each of these companies, and good scenarios that you can read and see the importance of chaos engineering. As you can see, the lot of big companies are already following this practice, which that you can understand how important this practice to your system's reliability when whichever customer you are working on. Going forward, so why do we do chaos engineering? So with the velocity that the companies are producing code, new features, they need to scale fast and smoothly. So whenever you add a new feature or something, or fix a bug, you don't know if that worked correctly beyond the uh, traditional unit testing and integration testing. So it will provide more insight to your system performance with what you have added. And as you all know, microservice architecture is very tricky. It's very tricky to see the issues because there could be tens of hundreds of services depending on each other, and everything is wired, everything is a network. So it is important to see what would occur to a system if any point of this fails in any way, to know about your system. And it is a known fact that services will eventually fail at some time. So the other important fact is dependencies on other companies. Like as example, the Netflix had a dependency on AWS because their region went down. They had a very large service disruption. So you need to think about those things and engineer your solution to withstand those failures. And by reducing amount of outages and downtime, you will eventually save more money, and it will the practice will prepare your engineers for real world scenarios that can occur in your production system. So other important things are to so these on-call engineers, they can be trained or prepared for different kind of outages, because in a normal system, let's say with a good reliable system, a failure would occur very rarely, say twice a year. So even you have on-call engineers, they might not have anything to like keep practice on these failures. So it's good to have this kind of failures simulated over the time, that they have good practice to recover from it very fast. And it also helps because you can develop most features or anything when your system is always failing, continuously failing. So that will force the engineering teams to do what they do best, fixing problems. So they will eventually fix the problems and make your system more resilient to failures. And also when doing architecting a system, because this chaos engineering has brought the failures that was in way back in our visibility, because they occur very rarely. So now chaos engineering has brought these failures to forefront, that you will see these failures every day, every hour. So everyone would think on working on getting out of these failures reliably going forward. So I will explain about Chaos Monkey a bit. The imaginary situation of say Chaos Monkey is like, think of releasing a bad monkey, naughty monkey, into a data center. So it will destroy the data center by like pulling network cables, biting down plugs, throwing out stuff everywhere, and it would be a mess in the data center. So this is what a chaos monkey do. So in Netflix, what chaos monkey did was it was deployed to a production cluster, and it brought down running instances, random instances very frequently. but within business hours, so that there was someone to attend to it. So so in the data center scenario, if you think about that, so how we prevent this monkey from destroying our system. So we don't get the chance to throw monkey out from the data center. You have to keep the monkey in the data center, but you need to prevent him from destroying this data center. So what will you do? That's the question that chaos engineering is asking from you. So typical solutions would be like covering up the network sockets, tighten up the cables with some cords so that monkey can't pull them off. Likewise, then that solution would become technical when we apply chaos monkey to your production system. So Netflix has came out with the army of monkeys, which is called Simian Army. They have created several applications. Chaos Monkey is used to simulate the instance disappearance of a system, and Chaos Gorilla is used to simulate availability region failure. Chaos Kong is to simulate availability region. Availability zone, and latency monkey is used to introduce latency to your system and see how your system behaves. Dr. Monkey is used to check your system's CPU, memory, and those things, and see the health of, let's say, a particular pod. And if it seems unhealthy, depending on the constraints, the Dr. Monkey will kill those pods. So there are lot of these kind of applications. If you go to if you search on Simian Army, and you will get a nice Wikipedia page which will have all these monkeys listed and described very simply. So these are very interesting applications that if you are willing to practice chaos engineering, these are very good applications that you can start with. So this is where my part ends. Is there any questions about the things that we already discussed?
Yeah, we can probably
questions. Yeah, so yeah, over to you, Keet.
Okay, so next up is principles of chaos engineering. So there are 5 different principles that are introduced in chaos engineering, and the main purpose of this is to teach people and tell people how to conduct a specific chaos engineering experiment. So if you look at the first point here, it talks about building a hypothesis around the steady state behavior. I'll be talking about each of these points separately, but for the time being, we'll just understand point by point. So at the first step, you need to build a hypothesis around a steady state of your software or the software system. And then the second point being, you need to understand that you can vary real world events, like the events that you see around you, around your architecture, around your system. You can vary them and see how your system will behave. And then you can run experiments in production. So maybe some people might be having this question: why production? It doesn't necessarily have to be the production environment, but production environment is the best environment to simulate the actual users traffic, the variations of traffic. Anyone can have a green field or a blue field environment or a testing environment where you can induce synthetic data or synthetic traffic and then monitor it, or induce chaos. That might help you capture certain scenarios, but not the actual production traffic. Because if you take a system like Netflix, inducing a traffic coming from Sri Lanka, from India, from all around the world might not be practical enough. But if you take the actual production traffic, you can see how the system actually behaves when there are real users using the system. So that's point number 3. And point number 4 is automate experiments to run continuously. As Pubudu mentioned below, this is not just a one-time test. We don't have to test this once and say, okay, our system is good, we are all good. No, it happens continuously. Sometimes this chaos happens in different scenarios when certain users, like let's take for example Christmas Eve. Most people might be at home, maybe most of them are trying to watch TV or Netflix, something like that. At that point, you have a lot of users coming up. And at that point, maybe if something small happens somewhere, something might go down. Your system might go completely unavailable, things like that. And then what you need to know is, since you are working on production, the last principle here is you have to minimize the blast radius. You can't affect everyone by running experiments like this. No, you have to select a selected scope and then run this experiment. I'll be explaining each of these, and at the end of this, I'll be showing a diagram as well. And then we'll move on to the demonstration part. If we look at the principle number 1, this is building a hypothesis around the steady state behavior. On the left side, as you can see, the steady state is the state your system is in when it is considered steady. Like, let's say you have a certain set of users using your system, and your system is performing as expected. You are happy, the users are happy. You can consider something like that the steady state of your system. These are some examples given on the left hand side. So you can say that if your 5xx errors, the error rate is below 5%, you can say that it's a steady state. If your 90th percentile latency is below 500 milliseconds, these are just typical examples. But you can even say your operations count is above 10,000. That means you have more than 10,000 users using your system per second. So this is a steady state. Once you have built a steady state, then you can build a hypothesis around that. So for you to build that, you need to ask the what if questions. Some examples are, what if the load balancer breaks? What if the cluster goes down? What if the auth server breaks? Questions like this will actually question your system and make you like confused. Like honestly thinking, what if Redis server becomes slow? How would your system behave? You might not have a proper answer to that. So things like this is how you build the hypothesis around the steady state that you have. And if we move on to the principle number 2, this is about varying the real world events. So some of the real world events are like hardware failures, functional bugs, then state transmission errors. So there are a lot of errors like this. If I look at the last few points, so Byzantine failure. So this is where data inconsistency comes into play. And then race conditions. So these are, so from, we all know, like software engineers, quality engineers, all of us we have worked in different systems, in software systems, architectures, distributed systems. We have seen race conditions a lot. If we're having multiple requests and we are using the same database connection, or we are using different databases, we can see these kind of problems. But can we really test these using regular testing approaches? No, these are experiments that needs to run continuously and detect continuously and fix continuously. So this is why you need to vary real world events. And then you can run experiments in production. So this is like simulating the failure of an entire region or data center. So that could be like, as Netflix was trying, we can say the AWS region or the data center is down. If we simulate that, how would our system behave? So there are different examples like this. I'll go through a few of them. So you can partially delete Kafka topics over a variety of instances and see how your system behaves. And then the third point being, you can inject latency between services. If you have a couple of microservices working in your system, you can actually induce a little bit of latency in different systems and see how would your main system behave, or how would your main system work. And then there are different levels like this. If you look at the end, you can also do time traveling. For example, you force the system's clock to be out of sync with each other. Just imagine if your system is using the system's timestamp or time, the clock of the system. What will happen if it goes out of sync? And you can simulate IO failures, and you can max out the CPU cores of your pods. Things like this could happen. And then you need to automate experiments to run continuously. The practice of chaos engineering is a long-running process and a labor-intensive process. So when you are running these automated experiments, you need to see, okay, how to like what kind of time does it take to detect this. So these are the kind of measurements that you need to make when you're running a system continuously and when you're automating these experiments, time to detect, time for notification and escalation. So like time to public notification, how long does it take to inform the public and things like this. And then if we talk about principle number 5, the last principle is you need to kind of scope these, the blast radius. You have to minimize the blast radius. So when you perform a chaos experiment, always remember to identify metrics like the following, because you need to make it contain and you need to know that not everyone is affected by this. So you need to understand who is impacted by this and how many workloads and what functionality is impacted by this. How many locations, like it could be the Asian region or different regions affected by this, and many more. So these 5 principles will actually teach you how to run and conduct experiments the way you want. So this is a typical example where users can, we can have a chaos experiment running only to 1% of our users, and the 99% of our users can be having a normal version of this. So this is a typical example, like we can use canaries or a different namespace or a different region to run this experiment on. And then, so this is the diagram. Let me take a laser point and point this out. So if you have a look at this diagram, at the first step, you need to identify the steady state. And then with time, you need to form all the hypotheses that you can bring up. Like ask the what if questions. What if the X service goes down? Things like that. So with that, you have to pick one of the hypotheses and start the experiment. Let's start with the right-hand side of this. So when you're starting the experiment, you need to know that you need to start small. You need to scope the experiment, identify the metrics, and notify the organization. And if you go to the right-hand side of this diagram, if the experiment stays in the steady state, that means it is a success and you can scale up and repeat. So that means you can start again with a bigger blast radius or a scope. And then if it violates the steady state, that means it's a failure. You can fix it and run again. And you need to have this kill switch to abort the experiment. In case of something like this, you need to have a kill switch that will easily abort the experiment. So this is a simple way of running chaos engineering experiments. So let me jump through to a demonstration that we have done and show you how these systems can work in real production systems. Hold on. Yes. So if I show you this dashboard, you can see that we have a system running in a Kubernetes environment, and we have a service called SRE automation backend. And so currently it is running on 5 pods. So if you have a look at this diagram, this one shows that there are 5 different pods running continuously. And for that same application, we are currently inducing a little bit of traffic. This is a simulated traffic. This is not real user traffic because this is a demonstration. So as you can see, there are 5 pods and each of these pods are getting somewhere around 6 to 7 requests per second. And even the latencies are somewhere around 1 second. There are spikes, but this is a valid demonstration, like a real user scenario where you can see a steady state. It's all in a single line kind of a environment, and you can see the pods CPU usage, the pods memory usage. You can actually see aspects like this. Now, let me show you how many pods are running here. So in this, we are using the namespace called reliability. And as you can see, we have 5 different pods running. And each of these, if you look at the age of these pods, they are like 4 hours old. That means they have been running continuously for 4 hours. Now, let me show you how we can induce a chaos into this. So for this, we are using a tool called the chaos mesh. This chaos mesh is a tool that allows us to inject chaos into Kubernetes environments. Like there are different levels of chaos experiments that we can conduct. So there are pod level chaos that we can induce, network chaos. I'll talk about these things in a little while. So for this demonstration, I'll be showing a pod level chaos induced into this Kubernetes environment. First of all, let's have a look at the configuration that we have put. This is a simple YAML file that we can apply to our Kubernetes environment, and for our demonstration purposes, we'll look at the last bit of this, which is highlighted. So the action that I'm trying to perform here is a pod kill. We have a perfectly running system right now with a proper user traffic, but I want to kill the pods now. And I want to kill it in a fixed percentage. And I want to kill 60% of the traffic, like 60% of the pods. So that means this will be running where it is killing 60% of the pods. And as you can see in the bottom, it will be running every 1 minute. And with a tool like this, we can, as I said, we can minimize the blast radius, and we can actually specify saying, okay, run this on the namespace of reliability. And then even on the namespace reliability, run this on a specific application only. So this will not affect all the applications. We can scope this into a certain limited service running in Kubernetes. Let's try and induce this and see. So I'm going to apply this podkill YAML file. It'll take a bit of time to reflect, but by that time, let's have a discussion about what other kinds of chaos that can be induced into this. If we look at the dashboard, we will start seeing a different level of measurements, because we can see that the pods have been started to kill. If we take the last 15 minutes of this, we can see that at this point, the pod, like 2 pods have been down. Since we have 5 pods, 50% is assumed to be 2, or sometimes it could be 3. So at this point, we can see that 2 pods have been killed. Just for the sake of looking at the pods, let's have a look at all the pods in the namespace right now. You can see that 3 of the pods have been killed and they have been restarted. So their age has been 40 seconds now, and the other 2 are running in 4 hours. So this will be running continuously every 1 minute. If this is happening every 1 minute, we will give it some time and see. Then we can, of course, start seeing the variations in different metrics like this. And then we can identify, okay, what kind of problems will occur if certain pods go down from time to time. How will our system behave? And looking at our latencies and the request counts and the CPU usage, how would our system behave? How would our users feel if the pods go down from time to time? So things like this are important to understand. That's why we have these kind of chaos engineering experiments. And if we have a look at the different types of until it comes up into a proper metric, like let's give it a few minutes. Till it comes up, I'll explain a little bit about the types of experiments we have in this toolkit. There are other different toolkits as well that you can use, but for the demonstration, we are using the chaos mesh. Here, of course, you can try the pod chaos experiment. So this is what we are trying to do. You can do this in different levels. For example, you can run a pod failure. What happens in a pod failure is you can say you can kill a certain number of pods. You can kill 3 pods, and you can ask the chaos mesh to not make them restart for a few seconds. Like it'll try to restart, but it will not be allowed to start up again. So we can say that, okay, keep it down for, if you look at this example, keep it down for 30 seconds. That means Kubernetes will try to restart new pods, but the chaos mesh will not allow them to start. That's called a pod failure. And similarly, we have a pod kill. This will just kill the pods. And then we have a container kill configuration. And we have different levels of configurations like this. And this is just on the pods on the Kubernetes cluster. If we look at other kinds of experiments, we have network level experiments. We call this network chaos. If you look at the different types that we have, we can do a network packet loss. So if we have like thousands and thousands of users using our system, what if certain packets get dropped in between? How would our system react? Something like that. We can also induce a certain level of network delay. And then we can induce network duplicate packets. What will happen if our packets and requests gets duplicated? And you can even corrupt the network packets. So based on these different levels of experiments, you can try out different scenarios and experiments on your production system. So if this is running like, let's say, every 10 minutes, you might be able to see, or maybe customers complaining, or you might be able to see or tackle problems that you have not seen before, things like that related to the network infrastructure. And there are some other types as well. I'll just briefly go through them because we're running out of time. There's a stress chaos. This is where you stress your system using multiple threads kind of a approach, where you can ask the chaos mesh experiment to burn a lot of memory, and you can ask them to burn the CPU cores. So when that happens, your pod will run out of memory and pod will run out of cores. How will it scale if something like that happens? Then how would your system react? How would the latencies increase? You can see things like that. And then we have time chaos. This is the thing that I said about time traveling. You can change and shift different times and offsets. IO experiment is if you are having some file system writes, IO writes or reads, you can impact that by doing a IO chaos experiment. And there are different other levels like kernel chaos and DNS chaos. I'll not jump into all of these, but if anyone is interested, just Google chaos mesh, and you will be able to see how we can run this chaos level of experiments on your own production systems. Now, since we have had a look at these different kinds of experiments, let's have a look at our demonstration right now. So we'll start from the pod count. As you can see, certain pods have been down for certain number of times, like it is getting down. And then in the meantime, if you look at these the request counts that are coming to each of the pods, you can see that certain pods are getting, now it has been getting around 7, but since certain pods are getting killed, you can see that some of the pods are getting around 15 requests. This is just a simulation. This will not show a high level of latency because these pods can handle a lot of traffic. But with this, you get the understanding. You get the understanding that we can induce different levels of experiments and see how certain pods, how certain systems will behave. But one of the significant things that are visible here is you can see that once these things start dropping out, you can see that the CPU usage of the pods and the memory usage are increasing. And if you look at the overall node level and the cluster level metrics, you can also see that there's a huge change, a variation in the CPU usage and the system CPU usage and the process CPU usage. All of these are occurring because we started inducing the chaos experiment. So you can see a clear difference in the steady state that you have in your system and how it has impacted these levels. Yes, now I will kill this. I will actually stop this chaos because I want to show that once the chaos is stopped, how will the system again come back to the steady state? This will be the last part of the demonstration. It'll take a bit of time to come back to a steady state. So that, of course, we can show at the very end of this presentation. So now I have stopped the chaos experiment, and it should start having a steady line in a few minutes. In the meantime, we can jump back to the presentation and have a look at the next slide. Yes. So we will have a look at the challenges that people face or the organizations face when you're trying to do chaos engineering experiments in your production systems. So these are like some common challenges. There can be many more as well. If you look at the first point, sometimes you might not have time or flexibility to simulate errors or disasters. So like the time limitations and based on the feature delivery speed and the capacity in your teams, you might not have that kind of flexibility to do these things. And then teams will always be spending their time fixing things and building new features. So it's like people, these are the questions that people say, like, do we need to keep on fixing things or building new features? Or like, if this happens every 10 minutes, that means we can see failures every 10 minutes. Should the developers start just fixing reliability and not features? These are some challenging decisions that people have to take. This is not only related to chaos engineering. If you even perform a different kind of experiment or even QA exercises, you might see challenges like this being faced in engineering organizations. And you can also see this can be very political inside the organization. Some people might like this, some people might not like this, some people might like to lead this or things like that. And the cost involved in fixing and simulating disasters might be a little bit high. Because if you look at, if we try to induce chaos engineering experiments into a certain subset of users, that those users might not like it, but it might be costly as well. We might have to allocate a different data center for recovery. We might have to allocate separate engineers and pay them extra to work extra hours to run this experiment, things like that. And there are many more company matters that build up the resistance in organizations when it comes to running chaos engineering experiments. This comes to the end of our presentation. But before I conclude, let me show you how the system will come back to a normal level. This might take a little bit of time, but as you can see here now, again, the pod's CPU usage is coming down a little bit because we have stopped the pod kill experiment. And if you look at the pod's memory usage also, it's coming down to a normal level, which is around 4 GB. So it has risen to around 8 GB. And the usage of cores in a pod has been risen to around 3 to 4 cores in a pod. So these are the kind of experiments, and this is just a simple demonstration for you to see, okay, once we induce something, we can see a difference in the metrics and the request counts and the latencies. Yeah, that concludes our presentation and demonstration.
I think we have a message from a guest.
Yeah.
No, we used a built-in small Spring Boot application to simulate the traffic, and we were doing this experiment on that dummy service.
Yeah. So if I repeat the question, also the question is, in the demo, any specific tool you use to simulate multiple HTTP requests, or is it a part of the Chaos Mesh? Chaos Mesh is only a toolkit that is allowing us to run chaos engineering experiments continuously. So in this, we have actually spin up a Kubernetes cluster, deployed these dashboards and the metric collection systems, and we have deployed a certain service. And from a different side, we are inducing the traffic so that we can see the demonstration like live with real user traffic. Chaos Mesh is just a toolkit that will help us do the experiments.
And to add to that, so if you have a question, if we should start chaos engineering, the question you should ask yourself is that if your system is reliable enough, that if it already has known failures regularly, then chaos engineering is applying chaos engineering will not give any better results because you already have failures. So when your system is quite apparently reliable, then you can apply chaos engineering principles to see the unseen parts of your system. And also it is important to have a good set of metrics and a visualization platform, something like this. Otherwise, you won't be able to see how your system is behaving. So I think that's it. Is there any questions from any of you you would like to answer?
If anyone is interested in knowing more information about this, feel free to ping us or reach out to us on Facebook or in LinkedIn or even through the company corporate site. We'll be happy to help.
Okay, it looks like nobody has any more questions. I'm sharing Pubudu's and Keet's email addresses. Of course, the creatives knows them, but if anybody who's joined from outside are interested in getting to know some more insights about chaos engineering, they can email Keet and Pubudu and find out what they want to know, get answers for their questions. If there are no more questions, we can wind the Tech Talk up. Thank you very much, Keet and Pubudu, for the very informative Tech Talk today. And we'll meet everybody in another Tech Talk pretty soon. Thank you and goodbye.
Thank you all for participating. Goodbye.
Goodbye, guys.